starting streaming and recording simultaneously after I discovered last Thursday that my videos went off into somewhere and I could not get to them anymore because YouTube had changed its streaming process. So I am simultaneously streaming and recording to my local machine. That way it isn't going to happen again, hopefully. But I wanted to make sure that it's going to work. Okay, it appears to be going. It says excellent connection. You guys are my witness that I should actually be streaming this time. So there, it appears to be working. So excellent. All right, then if there's no homework questions, logistical things, Thursday is no class. I will be attending a conference virtually, but there are office hours that afternoon from 3:15 to 4:45 like usual. That way, if you want to pop in and ask questions, or if you want to just come and work on your homework, in office hours and then, grab my attention if you run into problems. Folks do that sometimes too, and that's totally fine, whatever is going to be most useful for you. I did forget at the end of last class, I realized to talk about the article that I had posted, and that memory of having forgot haunted me all weekend. Like it showed up in my dreams. Like I was telling you guys about this article in my dreams. So I am going to not forget today, otherwise I will be haunted. So, this is an article that has nothing to do with statistics per se, except that it has a really great example of the issues that we were talking about at the end of last class with respect to type 1 error and type 2 error and power in sample size. So, can I give you the background why I picked this article? It's a story. A little story time with Lisa on a Tuesday? Okay, why not, right? So, once upon a time, I was a psychology major taking a 400 level social psychology class, and we had to do a project involving something where we got to pick the topic. And this was, I'm trying to do the math in my head, 1998 or so that this was happening, and a book was recently published about emotional intelligence, EQ as opposed to IQ. And so I picked that as my topic. And one of the reasons I picked it, I'll be honest, was because there was a thing on Oprah about it. The author of the book was on the Oprah Winfrey Show. And he was describing the results of a particular experiment that's reported in the book, that's the focus of this paper, the classic delay of gratification paradigm. Have you seen this before, anyone? Okay. So the few people, not everyone. So the premise of it is basically you grab some preschoolers, you put them in a room, and you make them wait for some sort of reward. You say, you know what? I'm going to give you one marshmallow right now, or if you can wait until I come back, then you can have two. And they measure how long it takes before the kid caves, basically. And the longer that they wait, or if they're able to not eat the first marshmallow upon seeing it, that's supposed to be delay of gratification, a measure of executive functioning, impulse control, something along those lines. So Oprah did the experiment on her show, and of course it was too cute to handle, like all the children like, doing things like this to try and block their view of the marshmallow and all that stuff. And according to the book, they did a follow-up study on the children in the original experiments, and those who were able to delay gratification to not eat the marshmallow longer had higher SAT scores when they were in high school. So delay of gratification had this sort of forward predictive validity thing, right? So that's what it said in the EQ book. And being a good little scientist, I decided to go dig out the original article. Turns out they left out 75% of the story. So here's the rest of the story. And I remember reading this article as an undergrad and getting to this particular table that I want to show you guys and going, oh my God, they cheated. So I will elaborate here 1 second. Let me get to the table in question. It's table 4 right here, this little table right here. So question before I dive in, but didn't it turn out they weren't measuring what they thought? They were measuring something related to privilege? Quite possibly. Because the results that were reported in the book were a much selected version of what actually happened. So here are the Pearson correlations between delay of gratification and SAT outcomes in the same children across the 4 conditions of the experiment, where they varied in whether or not the marshmallow that they were trying to not eat was visible and whether or not they gave children some sort of strategy suggestive to help them delay gratification. So this is the correlation. Can you see where I'm pointing here? This 0.42? That's the correlation, and the 0.57 that made it into the book and that they talked about on Oprah. There's a positive correlation between delay of gratification and SAT scores. Hooray, hooray! Now let's move over two columns in this table. And what do you see the correlation with SAT verbal being in this condition? Negative 0.4. The same magnitude. However, it doesn't have a happy little star by it. Do you know what the stars mean? You do now, right? Here's your key, the little stars. 1 star means p less than 0.05, and 2 stars means p less than 0.001. So I don't have a star by this correlation of 0.4, but I do have a star by this correlation of 0.4. Strange. Now, why might that be? What makes them different? Researcher bias? Well, the one that's positive was certainly consistent with their hypothesis that the idea that delay of gratification could lead to worse outcomes was certainly not expected. But it's actually a bias that's introduced in terms of who was able to come back. How many people came back? The last row of the table here. Sample size. There's 35 people that they got a hold of in this condition, but only 14 in this condition. So even if the people that they got a hold of and agreed to send in their SAT scores were a completely representative subsample, which, okay, no, but let's just pretend for a moment, 14 versus 35. Now, what did you learn about the probability of rejecting the null hypothesis? How does that relate to sample size? More people is better. Yes, very well said. The more you have, the more likely you are to find a given correlation to be significant. More people leads to more power, a greater chance of rejecting the null hypothesis if there is an effect to be found. So for instance, if the effect to be found is of magnitude 0.4, I have a much greater chance of rejecting the null hypothesis if my sample is 35 than if it's 14. To be more specific, let me go back to the power tables here that we looked at last time. Correlation of 0.4. If I have only, 14 people versus 35 people? Is that right? I'm trying to remember. 35 and 14, yep. So in the 0.4 column, with 14 people, I have about a 25% chance of saying that a correlation of 0.4 is actually significant. With 35 people, I have a 2/3 chance. So the fact that the relationship that they found only held in one condition, and that a relationship in the complete opposite direction of equal magnitude was found in another condition, was conveniently not described because it wasn't significant. So to me, this is a little bit disingenuous and suggests that if you eat the marshmallow or not, the jury is still out on what's going to happen to you. So I can't pretend to be a social psychologist. That's someone else's job. But what I can do is draw attention to the fact that this negative correlation of 0.4 should not be ignored. Just because it's not significant because of the sample size. And I don't know to what extent that there could be something nefarious here, like they deliberately got fewer people to underpower these. I suspect that is not the case, but it wouldn't be the first time that people stack the deck in your favor or against you, against finding things. So that is why I wanted to show you this article. A very clear demonstration of the effect of sample size in determining significance. So there's three things that you can do to have more power to find an effect. You can get a stronger effect, so a stronger correlation in this case. You can get more people to find it. And the other thing you can do is increase your alpha level. Make it easier to find something to be significant if you move in the goalposts for where unexpected starts. So for instance, an alpha of 0.1 will make it easier to declare something significant that has an increase in your power. It just comes at the cost of an increase of false positives. So, all right. Questions or thoughts on this example? My social psychology instructor was not thrilled that that was like the main point of my presentation, that there was differential statistical power, but you know, I got to do me, right? That's how I roll. This was helpful. I'm glad you liked it. So my hope is that when you start to read articles in your field, you can be a bit more critical of some of the nitty-gritty and not necessarily trust what people say in the discussion section, that you'll be able to go to the data that they're drawing conclusions about and decide for yourself whether or not you agree with the conclusions that they've made. Because you, my friends, are the ultimate peer reviewers. Peer reviewers just means that two people were happy enough with your paper that it got accepted. It says nothing about the universe of potential people who might read this. Do reviewers not look at the table? That's an interesting question. Not all reviewers are statistically savvy. They would claim perhaps that their area of expertise lies in the content of the article, and they would trust some other reviewer to review the methodology and to be the gatekeeper with respect to whether or not what they've done is okay. That's why you guys are the peer reviewers, always. Just because it's published doesn't mean it's any good, and just because it's not published doesn't mean it's bad. There's nuance everywhere. All right. Other thoughts, questions before we change gears? Okay. Then I don't have to dream about this article anymore.
Actually, I have a question, Lisa.
Sure.
Yeah, so if we come across a situation like this when we run our own studies, is it better than to, like, if we try to make the restriction less to find something, does that make the results more valid? I don't know, for lack of a valid probably isn't the right word, but is it a better study then?
I'm not sure I understood the middle part. What are you doing to make it, to change things? To make a
Because
restriction less, you said? I'm not sure what that means.
yeah, so you said there's three ways to make, like, address the issue, like to make it more less restrictive, to get more samples, and then the other, I forget the other one. But so let's say we can't get more samples. If we were to make the study less restrictive, would that be a better way to conduct the study?
Do you mean increase your alpha level?
Yes,
Okay.
that's, yeah.
So make it easier to declare significance, to declare there to be more area where unexpected is.
Yeah, to address the lesser sample size.
I think that is a reasonable thing to do, but that not everybody would agree with me.
Mhm.
Because historically, there's a bias towards preventing type 1 error at the expense of type 2 error. So there's a lot of literature, especially nowadays, about replicability and the idea that these findings may not appear in another sample. And the reason a lot of the time is a very high type 2 error rate. People conduct underpowered studies a lot of the time because it's very hard to get, in particular, small effects and to get enough people to have a decent shot at finding them. So It's type 2 error. Do you remember the conventional level that you were told to ascribe to for type 2 error? Anyone? You can give me hand signals or point 0.8 is the opposite. Point 0.8 is power, but right idea. Point 0.2, yeah, type 2 error, point 0.2. If you shoot for 80% power, that means at a given effect size that if you took the same sample over and over and over again, 80% of the time you would reject the null hypothesis that there's no effect at that effect size, and 20% of the time you would not. So right away we're setting up the idea that 20% miss rate is okay, but a 5% false positive rate is okay. So under that sort of, in certain situations, there's a bigger cost of missing something than there is of declaring something to be to have a false positive. I think if you can make the trade-off as to what is relatively more a worse outcome, then I
Mm-hmm.
think it's a reasonable thing to increase your alpha rate in small samples. But focusing on effect size and not necessarily just that barrier of significance is probably the best way to go forward. So like the problem with the article was that they said our effect was positive, delay of gratification was associated with higher SAT scores, and all the other correlations were non-significant. It's like it's that sweeping of the opposite effect
Mm-hmm.
size of the same strength under the rug that I object to. Oh, it was negative, but it's non-significant, so we can just ignore that complicating part of the story. So
So I guess just to clarify, then what you're trying to point out is that even if a number comes out non-significant, it's also important to see what it means on the overall
effect
study.
size matters.
Yeah. Okay.
Yes. Yes. Effect size absolutely matters. Whether or not that effect size is significant is a function of sample size.
Okay. Thank you.
Good questions. All right. Anything else before we switch gears on this topic? Okay, then I gotta tell you, I'm really excited. I've only had one cup of coffee today and I haven't even gotten started on this, but I'm really excited. Do you know why? Because it's model day. We get to start talking about models today. I know, raise the roof. We can all do our little happy dances. This is more tuition dollars at work. You get to see my happy dance, and the people on YouTube don't. But no, for reals though, linear models run the world. This topic is so transcendent across everything else in statistics that it makes me happy to be able to introduce this to you because it's a whole new world. It's so useful and pervasive. That's why I'm excited for you. Question. Okay. All right. So note to me, noted. Okay. So we're getting to start lecture 3, general linear models with one predictor. That's where we are here. So let me get this thing started. First off, we need some new vocabulary. So we're going to get into notation and vocabulary big time. We got to have some new words first to talk about stuff. But before we dive into that, just a brief review of where we've been and where that places us in a broader picture of doing quantitative analyses. So what we've covered so far, being able to describe one variable at a time, and a couple examples of inferential tests about a variable's mean. So one sample z, for instance, if you want to compare a sample mean to a population mean, and you know what the population standard deviation is supposed to be, swap that out for a t if you don't. We also did bivariate association, so that's lecture and example 2. So Pearson's R for linear relationships between quantitative variables. Spearman's rho for rank order variable relationships, still assuming linearity, and Pearson's chi-square for relationships among categorical variables. So what if you have a relationship between quantitative variables that's nonlinear? Could that happen? Absolutely. Does Pearson's correlation have anything to do with that? No, it's not designed to capture that. We need a model. Likewise, the pairing of nominal and quantitative variables. There's no way to do that with a simple correlation because the difference between the Each possible category in nominal variables has to be taken into account. We need a model. And the other reason we need a model is introducing, say, a third or fourth variable. Like, what is the relationship between delay of gratification and SAT scores after you control for the parent's socioeconomic background? Right? Questions like that. Do these two things go together for real, or are they just proxies for some other third thing that's driving both? Questions like after you factor in require a model. So there's lots of reasons why models are going to be useful for answering research questions. What I'm trying to do in this lecture is to introduce models from a perspective of things you already know. I'm going to show you how to fit a Pearson correlation in a model, because that way the concepts are things you already know. It's just the notation and the language around it that's new. But then we'll take our model and we'll trick it out. We'll add nonlinear relationships, we'll add nominal variables, we'll add extra predictors so that you can talk about the net effect of one variable versus the other. We'll get to all that cool shit, okay? All right. So the process then of quantitative analysis, like we've just scratched the surface of what one would typically do in a real life data analysis. So I have the steps here of what I think of in conducting an analysis sort of from scratch. Step one is to get the data. Now that could be a whole year or 2 year or 3 year effort to get the data, but I'm sort of skipping over that aspect of it. Likewise, I'm going to be agnostic as to the design of these things. How to design a study to collect good data is a whole separate set of classes and concerns that I don't get a chance to talk about here. Inputting the data into statistical software and verifying its accuracy. You guys know how to do that now, right? You can run proc import, and maybe it takes a few tries before it cooperates, but you can get there, right? Well, proc import and import in stata, they have all different flavors for all different kinds of data. You've done Excel, but you would just change one or two keywords to import SPSS data or stata data or an access database or anything like that. The procedures are all sort of the same, just different keywords. We would then describe data. So knowing what kind of variables you have is going to inform what kind of models you need. So whether or not something is a categorical variable or a quantitative variable, those are sort of the main categories. But within that, if it's a quantitative variable, is there a boundary? Do you have sort of, is it bounded between, say, 0 and 1 like a percentage, or is it a count that's bounded at 0? If it's a categorical variable, how many categories do you have? How many people are in each of the categories? Because if you have, say, a 3 category variable, is what you thought it should be, but it turns out there's only one person in one of the categories, you functionally have a 2 category variable. You're not going to be able to do anything with that one person in the 3rd category. So just getting a sense of the landscape of your data is a really important first step, because that's going to dictate the right procedures to follow and to make sure that it's accurate. From there, it's all about models. So it becomes an art, not just a science, but an art to be able to figure out how to represent research questions as linear models, how to be able to make it so that the output tells you the answers to the questions that you have, and if the output doesn't directly tell you, to figure out how to combine the pieces of the output in a way that does. That's the process that I get really excited about, because I see that as infinitely useful in being able to use quantitative methods for reals. But it's not just a one-step process though. There's always a process of fitting a model, see what happens, think about things you should also consider, fit another model, see what happens, think about other things, and so it's a very iterative process. What you read about in publications is like the most streamlined, sugar-coated, like I ignore all the forking paths, like I'm going to pretend like everything aligned perfectly on the first try and write it up from that perspective. That is not what happens in real life. And just a little bit about vocabulary. When you're writing results sections describing the results of models, we don't say I ran a model, I ran an analysis. That's okay to talk like that, but it's not formal enough writing. You would say that you estimated a model or that you conducted an analysis. So try not to use informal language if you can help it in publications. So more about language. In order to talk about how variables should go into the model to address research questions, we have to segment them into two purposes. And I've been using the names X and Y up to this point to talk about, say, correlation, like a positive correlation is as X goes up, Y goes up. There's a reason for that. X and Y in notation are going to symbolize the two roles that variables can play in a model, either an explainer or the thing to be explained. So on this slide, I have all of the synonyms that I could think of that go with this set of ideas. So in the notation that follows, variables that are thought of as predictors, explainers, are going to be X. So I may have X1, X2, X3. Variables that are to be explained, that are outcomes, those are going to be Ys. And I will keep that internally consistent so that you can get used to seeing things that way. And that's just not my choice. That's sort of a universal way that people use letters. X is a predictor, Y is an outcome. So predictor versus outcome is my generic preferred term. What is it that is going to happen is the outcome. What causes it to happen is the predictor. And which is entirely dependent on the way that you phrase the question and the timing of things. So in the article that I just showed you, delay of gratification being related to subsequent SAT scores means there's only one way that can work, right? Because you can't go back in time and cause your marshmallow behavior when you're a high school student. It doesn't work. But in other cases, you may have collected data simultaneously, and it's up to you what you view as the predictor and what you view as the outcome. If you have an experiment, so for instance, in the design of experiments class, and in many contexts where you are able to manipulate predictors, those are named independent variables or IVs. So this is a term, if you've had a methods class before, you've probably seen. Yes, maybe? IV and DV? Yeah, so I tend not to use those terms because they have a very specific meaning attached. An IV is usually something that is manipulated by the experimenter. It's people who are assigned to groups in a lot of times. So a treatment group versus a control group, as an example, that would be an IV. And then the corresponding outcome would be called DV, or dependent variable, in that context. And two more that show up in the context of regression models specifically. An outcome of a regression model is often called a criterion. That's used in a predictive context. So for instance, if you have some sort of formula that says, I've got your SAT scores and your undergraduate GPA, and I want to predict something about your future, like that something about your future would be called a criterion. But it's an outcome. There's just a different context. And last but not least, the term covariate. This is a term that has two meanings. It either means a quantitative variable as opposed to an IV. So for instance, if you have an experiment where you've assigned people to a treatment group versus a control, and you also measure, say, their previous exposure to something, right? The previous exposure to something might be called a covariate. In non-experimental context, covariate is used to describe predictors that you don't care about, but if you don't put them in your model, someone is going to yell at you. Every field has a predictor like that. I used to do work in cognitive aging, for instance, and those models were often focused on talking about predicting physical decline or cognitive decline, and you had to put in chronological age as your covariate, or someone would absolutely yell at you because you had to show that whatever you've measured contributes to the outcome above and beyond age. Socioeconomic status is a classic one in many fields. Is it similar to controls? Yes. A control variable is a covariate, is a thing that no one cares about, but you have to put it in the model. Now note that this is a semantic distinction. One person's control variable is someone else's career. Because at one point, the control variables were like, holy shit, this matters? And that was a paper. And then, 10 years go by and it's like, duh, this matters. You need to put it in the model so that you can talk about, holy shit, this new thing matters. So, predictor, you can be IV, you can be covariate, you can be whatever. It's X to me. Outcome is Y. Okay, with me? Okay, can you think of any synonyms that I should add to my list that you've heard before? Or other words you're not sure which side they go on? Okay, so in my class, it's predictor and outcome. So here's some examples. Let's practice. So this will be the audience participation portion of the program. I'm going to be eagerly awaiting the chat window here. So I want you to do two things for each of these sentences. I want you to identify which variables are the predictors and which variables are the outcomes. And based on how the question is phrased, try to guess how they're measured. Is it a quantitative variable or a categorical variable? So first question, to what extent does positive feedback improve performance, speed, and accuracy more than neutral feedback? So what do you think is X? I'm going to open this up so that I can type in it. 1 second. Predictors. Chat window says predictor feedback type 2 levels. Yes. So we'll say feedback type. And that is a categorical variable. More specifically, what kind of categorical variable? If there's 2 levels. Binary, yes. Bivariate means 2 variables, but you're close. Binary, yes. We'll put that there. Outcomes. What are my outcomes according to this question? And you're also allowed to unmute yourselves, by the way. You don't have to just type. Performance, speed, and accuracy. Yeah, so these are going to be quantitative variables. What kind of variable do you think speed's going to be? What do you think it's going to look like if you had to guess? I'll take gestures. Quantitative, not less than 0. If it's speed, it's often going to be positively skewed. We'll say above 0. And accuracy is going to be a quantitative variable. Has a very specific form, most likely. Is accuracy bounded or unbounded? Ratio. I'm not actually sure if accuracy is a ratio variable. It's at least interval, though. It's going to be bounded. What's the lowest that you can have in accuracy?
0?
0, yeah. And the most you can have?
100?
Yeah, 100% or 1 if it's a proportion. So we'll say that it's bounded 0 to 1. So why would that matter? In predicting variables like that, we have our Pearson correlation line, right? We have our linear relationship between variables. Well, we would have to find a way to tell the model, hey, that line needs to stop when you get to 1. And that line needs to stop when you get to 0 because you can't have scores out that. So in predicting outcomes that are bounded, we have to have a kind of a different line. We're not going to get a chance to talk about those models in this class, but I want to plant the seed that there are models that have that type of adaptation for bounded variables in them. Okay, next one. This is a tricky one. Is faster academic growth in elementary school related to more frequent reading to children when in preschool? What's my predictors in this? Yeah, frequency of reading. Couple votes for that. And any guesses as to how that might be measured? No idea. Could be anything. It sounds like it's quantitative, but it could be ordinal. Yeah, it could be number of books, amount of time. It could be I read every day as a 1, I read every other day as a 2, or something like that. So yeah, we don't know from the question. There's actually another predictor that is implied by the sentence. And this is one of my areas of expertise. The textbook that I wrote, Longitudinal Methods, seems like both could be predictors. This is a correlation type question. It is a correlation type question. Yeah, I was going to say time, but age, because it says growth, right? It doesn't actually tell me growth in what. So I don't know what the outcome is. I know that time is one of the predictors because you have to measure age in order to do that. We'll say age, grade, time. It's unclear. It depends on the design, how the design is, how long they're measuring. But outcome, I'm going to put here whatever is growing. So this is simultaneously a tutorial on how not to write a research question. I have a whole lot of practice in this area because I have helped put together dozens and dozens of grant proposals. And my job on the grant proposal was to read someone else's questions and try to figure out what that's going to look like in terms of a model. And if I can't identify what the variables are, it is game over for figuring out what the stats are. I got to tell you that much. So growth in something is the outcome. But that implies that time is a model predictor if you're going to have growth, because you have to assume, you have to be able to observe change. How about the last one here? How effective is teacher training for creating higher rates of positive feedback to a teacher's students? What do you think? What's a predictor here? We got 1 vote for training, 2 votes. Any idea how that's measured based on the question? I have no idea. Yeah, it could be binary. It could be that you're giving them training as opposed to no training or a business as usual training. It could be the amount of training that they choose to engage in. Like if they're working with a new system, it's how many hours they put into logging into using the system. I don't really know. What's the outcome here? I'll put a and I'll put a there. What's the outcome then? We have rates of positive feedback. Now, based on that, the word rate, is that going to be a categorical variable or a quantitative variable? Quantitative, and it's also going to be bounded, because a rate means that you are correcting for the number of possible opportunities where something can happen. You're creating a fraction. So you would have to have a rate that is bounded by 0 and 1 again. So we'll say rate is bounded. So there's actually one more issue in the last question that doesn't have to do with predictor versus outcome, but it has to do with level of measurement. At what level is the predictor measured? It's teacher training, right? What constitutes effective? I have no idea. Bad question. But it's teachers are the ones who are getting trained or not, or they're having different kinds of training or amounts of training. I don't know. But who is the outcome about? Rates of positive feedback to a teacher's students. So this kind of design where changes are supposed to happen at the group level and the output of those changes is measured at the individual level, that is a classic example of what's known as a clustered data sample or nesting. You have students who are nested in teachers. That is going to be my other classes to be able to address those sorts of designs, putting a plug in for why the world of multi-level models would be relevant to you guys. Because in such models, we have to be concerned with variability across students and variability across teachers simultaneously. So it's two different levels of analysis that would be happening in the models. So all the models we're going to be focusing on are assuming that all of the variability is happening at one level, that there's only one dimension of sampling, but that's not going to be true in a lot of real life settings, especially in education. Okay, thoughts or questions on this? Okay, thank you for playing. I appreciate the participation. So moving on then. Oh, I made it angry. There's nothing worse than a giant pink hourglass. It's like, no, I'm not going to move on. I'm just not. That's okay. At least I'm not stuck in an elevator. Did you guys
Hey,
hear
while
about
we're
that story?
waiting, oh, sorry.
Yeah, while we're waiting. Yeah, I'm trying to kill time. But
Yeah, just quick question. Why was rates, you said it's quantitative and we don't know exactly how. Why was I thinking like rates could be categorical? Like if you're rating first, second, third. I don't know. I guess it's because we don't know about
yeah,
what the
I
rates
think
is.
the word,
Okay.
if it were rating, you would be right.
Okay.
But my use of the term rate was implying a numerator and a denominator, like the number of times that something happened out of the
Got it.
number of like how length of the interval where you were observed, for instance.
Okay. Okay.
So
Let's
um,
hear about the elevator.
let's hear about the elevator. No, there was
Yeah.
a story. Some guy in New York City was picking up his kids and got stuck on his elevator in his building. It was 10 minutes before he was supposed to teach. I think it was an intro psych class of like 300 people or something. So he called into his own class on Zoom and gave his lecture in the elevator with his children while he waited to be rescued. No slides, no notes, just off the top of his head starts lecturing into his cell phone while his 8-year-old and 6-year-old, I think, were just sitting there. So that is a new like record in terms of being able to go off the cuff. I have had actually in the classroom where we were supposed to be. Um, our definition of hell, yes. Yeah, trying to lecture while your children are in the elevator without notes, that is dedication. But he had a test coming up, and if he didn't review the material, they'd have to reschedule the test. And so he had to make it work. So yeah, I once had the whole projector system shut down in the classroom where we were supposed to be, and I had to go cold. So I was like, all right, well, you guys have computers, you have your stuff in front of me. I'll see how well I remember my slides. Let's do this. So, yeah, at some point, you just got to make it work. That is like the official motto of 2020, just make it work. And I've killed enough time now that PowerPoint is back. So here we go. We're going to make it work. In terms of language, so in this class, I am not going to be assuming any kind of causal inference anything. Okay, so even though I'm labeling variables as x as predictors and y as outcomes, and that sort of implies that x's cause the y's, there are three conditions that have to hold in order for you to be able to start to talk about causal inference. That really it's x is driving y. X has to come first, temporal precedence. X has to be under complete control of the experiment. So you have to have random assignment to groups, and you have to be able to manipulate what X is. And you have to be able to eliminate all possible alternative explanations for the phenomenon. And that last one is the one that's the sticker. There is a class on this that you can take. It's called causal inference, and it's focusing on how you can get closer to something that looks like causal inference in quasi-experimental designs, because most of the things we care about in life we can't randomly assign, right? Like I can't take two twins from birth and make one of them a smoker and one of them not a smoker to see if smoking really does cause cancer, right? Like I can't do that. There's a lot of things we can't randomly assign. So the idea of how do you get closer to being able to say, no, this is a causal relationship in those situations is a whole nother set of topics in and of itself. In this class, I'm going to use associative language. So X predicts Y to me simply is describing a mathematical relationship between the two. I'm not saying that it couldn't be that Y predicts X. That could also be true. And whether or not we're phrasing it as Y predicts X or X predicts Y depends on the question. It depends on how the question is phrased. The question dictates what is a predictor and what is an outcome. And so associative, we can say that these things are associated, that one relates to the other, that as X goes up, Y goes up by this much. We can use that kind of language and just try to stay away from the causal word. One thing that is sometimes confusing is that these sorts of designs are also called correlational designs, meaning that all the variables are collected at the same time and they're expected to relate to each other, but we're not specifying what is driving what. You can have a correlational design that is analyzed by not a correlation. So that's an unfortunate term. It doesn't mean it's as restrictive as you would think by the word. So you can do other sorts of analyses on correlational designs besides just correlations. So what is often the case in designs where you can't control what's going on is that what people attempt to do is statistical control. So the example that I gave you earlier, does delay of gratification predict SAT scores after we control for parent socioeconomic background, right? That is a classic example of a statistical control question. What we're trying to do is to look at how these variables are related after taking out the part that's in common between them that might have to do with socioeconomic status. And so we put into the model all of the alternative explanations. Why is it that these two variables could be related? What do they have in common? And we put those alternative explanations into the model as additional predictors to try to factor out their influence in a statistical way, just not an experimental way. So that's what we're going to be focusing on in this class, associative designs and corresponding language. Okay? Deal? All right. So linear models. That's where we're at here. So we have to designate which predictors or which variables are predictors and which are outcome, and we're forming linear models with these. So what kind of model you need is going to be dictated by what kind of outcome you have. So we have quantitative outcomes, we have categorical outcomes, but then there's subtypes within that. This semester, all that I'm going to have time to give you is models that are designed to predict quantitative outcomes that are supposed to be unbounded. We're going to use the normal distribution to describe the variability of an outcome and to conduct all of the hypothesis tests regarding the effects of predictors on that outcome. So this is what's known as a general linear model. That word general has a very specific meaning, ironically. Yes, the word general has a very specific meaning. It means that we are using a normal distribution to describe the variability in the outcome that remains after we factor in the predictors. But just to put a pin in it, if you work in a research area where you're not going to have those kinds of outcomes, because quite frankly, those are actually pretty rare that we have a quantitative outcome without a boundary of some kind, every other kind of outcome has a model for that. So this is all the other kinds that are out there. I just want you to know that they exist. And if you're in a situation after this class where you have to analyze data for one of these other kinds of outcomes, I wanted to give you the right words to Google to go and find out what you need. So it's a combination of what kind of distribution you're saying describes the outcome and whether or not you need to transform the outcome that's being predicted to remove the boundaries. So that's what's known as a link function, is a special kind of transformation that happens through the model. So for instance, if you have a binary outcome, that's what's known as a Bernoulli distribution, and a logit link. Ordinal has a distribution for that, nominal has one, binomial has one, counts have all kinds of them. So just to put the pin in here, The class that I designed that I offered last spring, I hope to come back within 2 years, if not sooner. It's known as generalized linear models, where the ized means some kind of outcome that's not normal. And all of these models get covered in that class. So don't let anyone tell you that your outcome has to be normally distributed or that you can't analyze it. That is old school bullshit that is no longer true if it ever was. It's just a function of what models you have at your disposal. If all you learn is a general linear model, then you're going to have to try to make everything normal. But there's lots of variables that are simply never going to be normally distributed no matter what you do. And there are models for them. So these are the words to ask the Google about, or you can Google my class. So it was listed as PSQF 7375. It's a special topics class, and all of my videos, except for one or two where I somehow messed it up, are on YouTube, and you can check out that stuff. So I hope to see at least some of you there in the future. So what does a linear model mean to us? That word also has a very specific definition. The definition of a linear model is that it takes this kind of form where it is a constant times a variable plus a constant times a variable. It looks like algebra. So a nonlinear model would have like a log in it, or an e to the, like an exponent in it, a square root in it, something like that. So the fact that every term is added together, it's constant times variable plus constant times variable, that's what makes this a linear model. It's easy to get confused by that terminology into thinking that the only kind of relationships that we can examine are linear relationships, though. That is not true. So for instance, if I want to examine a parabola type relationship, like an upside down U, for instance, that's what's known as a quadratic term. If I took one predictor and put it in the model, and then I took that same variable and squared it and put that in the model too, then this linear model of constant times variable plus constant times squared variable, that would make my U. So even though the form of it is linear, we can have nonlinear relationships come out of this form. Likewise, the X predictors don't have to be quantitative. They can be any kind of predictor. And I will teach you how to create predictor variables that are appropriate out of ordinal variables or out of nominal variables, as well as quantitative variables as part of this class this semester. So, what are you going to be learning? Those of you who've had stats before, you might recognize some of the names that are in this bottom section on slide 8. Do these look familiar? Or you may see these in result sections. So in my humble opinion, the old school categorization that happens within the general linear model using these names just makes it confusing for people, and it makes it harder to learn because you're trying to represent these artificial boundaries between different kinds of models. So what's going to happen is that every time that we add a predictor that's a different kind, the name of the model is going to change. So if you have all of these models that we're talking about are predicting a quantitative outcome that's supposed to be unbounded. If you have a quantitative predictor, that is called linear regression. If you have a categorical predictor, that is called analysis of variance. If you have both kinds, that is called analysis of covariance, or sometimes regression, depending on who's talking. But we're going to use the same proc GLM or regress and stata for all of this, and the procedures that go into trying to put the predictors in the model are exactly the same. So the way that I approach this is that you're going to learn the general linear model, which means that you can put any kind of predictor that you want in it. We'll start with models that just have one predictor, and then we'll move to models that have more than one predictor. And these different names for different combinations of predictors are not helpful. But if you want to add to your list of skills, right, on the CV, your technical skills section, put down as many of these as you can fit. I know linear regression. I know analysis of variance. I know analysis of covariance. I know all these things. So all of this is a one-stop shop within SAS GLM or Stata Regress. So we're going to pick up really just one, maybe two packages to do the whole rest of the semester with. It's all going to be the same. Okay. Now, how many outcomes can we analyze at a time? This is another distinction that has to do with how models are described. We are going to be doing univariate models, meaning that there is one outcome per person in the model. The models that have more than one outcome at the same time are called multivariate models. Multi meaning more than one. And those models are also covered in the generalized modeling class. So if you have, say, repeated measures data, like you have, say, a pre-test and a post-test, and you want to be able to predict change from pre-test to post-test and to predict who changes differently, that falls under the multivariate heading. We're not going to get there this semester, but I can point you to where that stuff is. If you have data that is like that, or even more occasions, longitudinal data, where you follow people across ages or grades or time, come back in the spring. I'm teaching the longitudinal modeling class in the spring. And Farhan, I'm going to tell you, I'm sorry in advance because you're going to have to stay up until midnight if you want to come, because it's offered at 2 o'clock in the afternoon, times that were
Worth it.
decided before the pandemic was a thing. So, sorry, go ahead.
It's worth it.
It's worth it. Hey, there you go. Way to be obsequious. I like it. So yeah, so just letting you know that like what I'm going to teach you isn't going to cover everything that you're going to need in your lives, but everything that I'm going to teach you is a baseline to which we're going to add other stuff. It's like Legos, right? We have a nice little solid foundation of Legos, but if you want to have like Legos that have a propeller or Legos that have little people, or you want to make a car out of your Legos, you need wheels. Like we'll add on the extended pieces in further classes. So here's our very, very first model. Are you ready? After that big buildup, it's right here. Y sub I equals the red thing plus the blue thing. That's it. I'm going to use colors very purposively in these models. And so red and blue mean different things. So Y sub I, you've met that before, right? Do you remember that from when calculating means and variances? So that is a variable. Each person has a different potential Y value, so that's where the sub I comes in. This B looking thing is the Greek letter beta. It has a 0 subscript, and that means this particular beta has a very specific meaning. It is going to be called our intercept. Beta sub 0, I will call this beta 0. That's how I will refer to it. You will sometimes hear people say beta naught. I will not be calling it beta naught because what the hell is that? It's beta 0. And the thing to notice about this beta 0, it does not have an I. So it is not a variable, it is a constant. So beta 0 is going to be a number that is shared by everybody in building their predicted outcome. It's an intercept. E is something we'll get to in just a moment. But these betas, we're going to have a beta 0, a beta 1, a beta 2, a beta 3. They're known as fixed effects. And the idea is that they are fixed to one value for everybody. They are constants, not variables. So what does this mean? So this model is what's known as an empty model. It has no predictors. The sole purpose of this model is to provide a jumping off point for describing what is the best sort of naive guess for what any person's outcome is going to be, and how much variability around that best naive guess does the variable have. So the definition of the intercept is always going to be the same throughout this class and throughout all the classes. The intercept is the expected outcome when the model predictors equal 0. Always. At this point, there's no model predictors. So the expected outcome is just the mean. Let me put it to you this way. If I know nothing else about a person and I have to guess what their outcome is going to be, the best guess that I could make is to guess the outcome mean, because that's the one that's in the middle. That's the one that's most likely. So that's my jumping off point. If I know nothing else about a person, I'm going to guess that they have a mean for an outcome. And the job of adding other variables as predictors is to refine that guess. I would make a different best guess if I knew someone's age, if I knew their whatever status, their background variables, their procedural variables, anything that's capturing a person helps me to refine what that best guess is. So this is the worst that I could possibly do in terms of prediction, is I say, okay, everybody gets the mean. Now let's go from there to make it better. So in this case, what would beta 0 be if I were describing the variable with the blue line here? 0. Yes. What would beta 0 be if I were describing the variable as an outcome that the red line is conveying? Same, yeah, and the same for the orange line too. What's the difference between the red line, the blue line, and the orange line? Yes, I'll take gestures. I'll take this for height, which is how high the mean is, which is called likelihood, by the way, and this sort of gesture for the variability around it. So yeah, we also need to know how far off from the mean the observations tend to be. We need to know the variance. More variable, more flatter, since they are all normal? Yes. Yes. The more variable, the more variance is inside a variable, the flatter it is going to be. The further away on average from the mean any one case is, which is the standard deviation. So since we got to know variance, that's what E is for. The role of E is to try and describe for any person how far off they're likely to be from this best guess that we have defined as the intercept thus far. So E sub I is going to have a special name known as residual. You can also think of it as error. E sub I is everything that we don't know about a person. Why is their outcome the way that it is? I have no idea. E sub I is what's left. So up to this point, we've given each person a mean as their best guess. So E sub I is the difference between the actual Y sub I outcome that they got and the mean that we're guessing for everybody through the fixed intercept. E residuals are always going to have the same definition in this class and in every class. It's how far off your outcome is for real from the one that's predicted for you. How wrong is the model? That's what E is telling you. For each person, how far off is your predicted outcome from the real one? So if E is positive, your real outcome was higher than what was predicted. If E is negative, your real outcome is lower than what was predicted. So the variability across people in the E's is what we're going to start paying attention to. And the variability across people, when everybody has the same predicted outcome from the mean, is something you guys already know. This is variance that I'm talking about. So in other words, what used to be y sub I minus y bar, y for each person minus the sample mean, another way of saying that same thing is to stick E in there instead. Because that's what E means right now. E is how far off each person is from the outcome that is predicted for them. In this case, everybody's outcome is predicted as just the mean, but it's going to get refined when we start adding predictors. And even though I told you that the sample variance was S squared and the population variance was sigma squared, I lied. From now on, it's sigma squared. It's one of those things that shifts in the way people talk about it for no apparent reason. My best guess is that it's because we're using Greek letters for the other parameters. And so we're always talking about what we think the best guess of a population is, and we know that we only have one sample. So we're going to see betas, and we're going to see sigma squared E. But the key thing that I want you to hang on to is that when you have an empty model like this, the variability that is held in that E term across people is all the variability in the variance. All we've done is just recreate the variable's mean and the variable's variance. That's what our model is doing.
Can you
Go ahead.
repeat that again?
Yeah. So without any predictors in the model, what we have done is just recreated the variable's mean and the variable's variance. So what we care about is what is beta 0 going to be? It's going to be the sample mean. And what is the variability across people in these E's? As a set, what is the collective how far off each person's real outcome is from the one the model predicts? What is the variability of the E's? And if we don't have a more refined model, if everybody is getting the mean as what is predicted for them, then the variability of these E's is the same thing as just the variability in the original variable. It's exactly the same thing. So one way of thinking about it is like this is all the information that we have about the outcome in the sample. Let's see how much of it we can explain, how much of it we can account for with our model, and see how much of it is left over. So this E variance, sigma squared E, is the most variability that an outcome can have. It's all of it. And our goal is to try and make it get smaller. Make the difference between what the model says your outcome is and what the actual outcome is. We want that to keep getting smaller and smaller and smaller. So the empty model is the worst thing that you can have. It's the jumping off point for everything that follows. Okay, it's lagging again. All right, so let's put something in the model. Because I don't need a model to tell me what the mean and the variance are of a variable, right? I can just ask for that. But they represent a naive starting point for making better predictions for each individual. So here's a model that has a predictor in it. So we have a new equation here. Y sub I, the outcome for each person, so that's one column in the data set, is now a function of beta 0, which is still my fixed intercept. But we've picked up a new term in the middle here, beta 1, which is multiplied by x, another column in the data set. So x sub I is my predictor variable column. Y sub I is my outcome variable column. They both have i's because they both vary across people. Beta 1 is a slope. So other than E, like if I hid E with my giant pink mouse for a moment, this looks like 8th grade algebra. You learned about the constant and the slope. It was like y equals mx plus b back then, if I remember correctly. Does that sound right? Like someone just decided that those letters were going to be the universal algebra letters. Well, this is the same. It's a repackaging of 8th grade algebra. That's what we have here. The constant is the intercept, and the slope is beta 1. Beta 0 and beta 1 are collectively known as fixed effects. They are estimated by the data, but once you figure out what the value of these is, it's the same value for everybody. So beta 1 is a slope that is a constant number. That's why it doesn't get an I. Likewise, beta 0 is an intercept that is a constant number that does not get an I. And if I have two variables that both have a mean 0 and a standard deviation of 1, in other words, there is in a z-score metric, and I have a Pearson correlation between them of 0.5, I can use that information to actually calculate what my slope would be. It's the Pearson correlation adjusted for the standard deviation of y and the standard deviation of x. If both variables have the same standard deviation, that term drops and it's just the Pearson correlation. So the slope of the line that relates x to y is the Pearson correlation in this case. That's why, as I told you before, we're not doing anything different yet. We're just putting what you know, Pearson correlation as a concept, into a model. So we can start introducing models. Intercept then can be calculated as the mean of the outcome minus the slope times the mean of the predictor. So if we put the values in here, it works out to be 0. So the job of the intercept is to compensate for differences in the mean of the predictors. The job of the slope is to convey the strength of the association between the predictor and the outcome. But the value of the slope is going to be a function of the metric of each of the variables in question. So for instance, if x has a bigger range, if my predictor has a mean of 50 and a standard deviation of 10, but my outcome still has a mean of 0 and a standard deviation of 1, well, then the beta slope has to adjust. It goes from 0.5 to 0.05 to compensate for the difference in standard deviations. Likewise, the means being different, beta 0 is going to adjust to compensate for that. And the same thing would happen if I switched out the other two variables. So the thing about the slope is that you have to know what the units are to know what the number means. The slope's definition in this class and in every class is the change in y for a 1-unit change in x. Always. The change in y for a 1-unit change in x. So if x has a much bigger range, the slope has to be a lot smaller to talk about what the change in y would be, because a 1-unit change in x is huge. Likewise, if y has a bigger range, the slope has to get bigger to talk about what the change in y would be for a tiny change in x with a small range. So differences in what the variables mean are absorbed into the model because we're talking about what a unit is. The slope is always the change in y for a 1-unit change in x. So we have to know what a unit is to know what that means. Okay, there. That's a good place to stop. There's a teaser for you. All right, how are we doing? Okay, so the objective